Now we're going to do some more challenging problems than the previous example set, but the fundamental principle is the same. In this case, we want to find a fourth degree Maclaurin polynomial for this function. Now that function is kind of gross, so what I'd like to do is do long division on it, or, I mean, you can do long division. What I'm actually going to do is kind of do the little swap trick. So I'm going to say, okay, well, this is x plus 1, so what multiple of this would be a multiple of x plus 1? Well, that would actually be 3x plus 3 would be the multiple. But I don't have 3x plus 3, I have 3x minus 3, so I kind of have to balance it out. Because ultimately this resolves back to that. So I'm kind of playing, it's almost like making change, right? Like you're giving them the same amount, but you're giving it different ways. And then you split it into that, which gets you 3 minus 6 x plus 1 to the negative 1 power. So this is going to make our lives a little bit easier when we're taking the derivatives. So we're going to follow the same process that we did before. You start off by taking all the different derivatives. So we start off with the 0th derivative. Well, the 0th derivative is the function itself. That's 3 minus 6 is 1 to the negative 1. The first derivative, so that 3 is going to go away with the first derivative. So then we bring down the power, that cancels, and we subtract 1 from the power. And then we would have to do the chain rule. But by the chain rule, the derivative of x plus 1 is just 1. So we're doing the chain rule, but it doesn't really show up. It kind of vanishes there. So when we take the second derivative, we get negative 12 x plus 1 to the negative 3. We take the third derivative, we get 36 x plus 1 to the negative 4. And finally, when we take the fourth derivative, we get negative 144 with x plus 1 to the negative 5. So now that we've found the derivatives, the next thing we want to do is evaluate them at the center point. Now, this is a Maclaurin polynomial, so our center point is 0. So we're going to say the function evaluated at 0, well, that's 3 minus 6 times x plus 1. So this is x plus 1, or 0 plus 1 is 1. 1 to the negative 1 is just divided by 1. So it really doesn't contribute. This is really just 3 minus 6. You get negative 3. Which is a lot easier if you actually just use the original definition, because those terms vanish. You get negative 3 over 1. So I made that a little more complicated than I needed to. What you're going to find each time when I plug in 0 here, this just becomes 1 in the denominator. So realistically, all of these terms kind of just evaporate. You get 6, negative 12, positive 36, and negative 144, right? Simple enough. So then what we do is we use this setup. So we have x minus the center to the kth power. Well, the center in this case is 0, so this is just x to the k. And then this is defined by something we already found, divided by the kth term factorial. So following the template, you have the this term, or 0 factorial times x to the 0 plus this term over 1 factorial x to the 1 plus this term over 2 factorial x squared plus this term over 3 factorial x cubed plus that term over 4 factorial x to the 4th. So notice you're just following it, right? 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. And you're taking the value here and just plugging it in. That's all you're doing. And this simplifies, so 0 factorial is 1, so this simplifies, and x to the 0 is also 1, so this simplifies to negative 3 plus 6x minus 6x squared plus 6x cubed minus 6x to the fourth. It's kind of neat, right? You end up with all these sixes here. I actually didn't expect that. That's kind of neat. And so, I guess I should have expected that, because each time, notice that each time you're getting 1, 2, 3, 4, 5. So you're actually getting like the factorial scenario here. So it's only natural that it would end up looking like that. So this is your polynomial. It's your polynomial solution. Obviously you can rewrite that as you need to. So it's kind of interesting, because now instead of something that is a rational expression, you have it in terms of a standard polynomial, and near zero is actually going to be a pretty good representation, or a pretty close approximation of what you're looking for. Now in this one we are doing a Taylor polynomial versus just a Maclaurin polynomial. And again, they're the same. The only difference is that Taylor polynomials allow for an arbitrary center. So we're going to do the same thing. We say, all right, the 0th derivative is just my function. Well, in this case it's g. My first derivative is negative cotangent x. Let's see, negative cosecant cotangent x. So you have to do that, and then you have to take one more derivative because we're doing a second degree. And so by the product rule, you take the derivative of the first one, which is negative cosecant x cotangent x times cotangent x, and then you take the derivative of that, which is negative cosecant squared, so you get plus cosecant cubed x. That's pretty ugly. Let's rewrite that. So that's going to be cosecant x cotangent squared x plus cosecant cubed x. So I believe that's right. I am doing this off the cuff. I apologize. Now we have to evaluate this at pi over 2. So the function value at pi over 2 is just 1. Cosecant is 1 over sine. Sine of pi over 2 is 1. So, alright, now the first derivative at pi over 2. So that's negative 1 because it's negative here. But cotangent of pi over 2 is actually 0. So you end up with 0. And when you do this one, you get, again, that's 0, and that's 1. So you end up with 1. Because it's 1 cubed, so it's 1. Well, it's pretty easy, right? So I have my polynomial is 1 over 0 factorial. Now, in this case, it's not just x to the 0, it's x minus the center to the 0. Plus 0 over 1 factorial x minus pi over 2 to the 1 plus 1 over 2 factorial x minus pi over 2 squared. So in this case, 0 factorial is 1, that to the 0 power is 1, so you end up with 1, and then this is 0 times whatever, so it evaporates, plus 1/2 x minus pi over 2 squared. Now that's a really interesting thing, right? Because that's not a very, you wouldn't expect that. That's a very straightforward parabola. That's just, if you looked at this, it's kind of in the standard form. You say, okay, well this is a parabola that shifted pi over 2 over. It's scaled down by 1/2 so it doesn't open as quickly, and it's scaled up by 1. So you can take this and plot this against cosecant, and I think you probably get pretty good, because cosecant kind of touches sine at the top and then has those like almost like parabolic things, but there's those vertical asymptotes. So I think you get pretty good approximation there near pi over 2. But I would actually expect this to be pretty bad away from pi over 2. Now I might be wrong. I haven't plotted this yet. But I would expect this to actually degrade kind of quickly because it's just a little too simplistic for my tastes.